what is the triangle inequality? So the triangle inequality states that for any complex numbers z1 and z2, then the modulus of z1 plus z2 is going to be less than z1 plus the modulus of z2. Now what this is really saying is it's talking about our lengths of a triangle. Okay, so in this first case, this z1 is the length of one side, our length of the other side is z2, and that means our third length along here is just z1 plus z2. And that's saying that your length of your one side plus the length of the other side is going to be bigger than the length of your third side. The other thing to make clear here is that the equality case, so in here there is that equality in our less than or equal to sign, and this occurs, equality, when z1 and z2 are parallel and in the same direction. So that'll come a little bit more clear over on the next slide. So 3 examples of the triangle inequality for triangles with sides of lengths x, y, and z. The top example shows a case where z is much less than the sum x plus y of the other two sides, and the bottom example shows a case where the side z is only slightly less than x plus y. So as x and y are getting closer and closer to parallel, right, in these cases, then our x and our y, when we add them together, are getting closer and closer to our this bottom side, or the third side, which is x plus y. So each of the sides individually plus the other side individually is getting very close to the other one when you have parallel sides. The next thing to do is to try some problems with this, and we want to verify that our inequality actually holds true. So let's have a look at this here. So the very first thing we want to do is we want to look at z1 plus z2. Z plus z2 is going to be 3 plus 10i. And if I wanted to find the modulus of this, we get square root of 3 plus, 3 squared, sorry, plus 10 squared, and that is equal to the square root of 109, which is equal to 10.4. And so you use your calculator for that. Now, the next thing we want to do is we want to look at z1 modulus. Well, that's a 1. And that is equal to the square root of, we're going to have 3 squared plus 4 squared. That's equal to square root of 9 plus 16, which is the square root of 25, which is equal to 5. And then if I do z2 modulus, what do we get for this one? Well, that's just going to be 0 squared plus 6 squared. Oh, that's some fun bit of technology. Plus our 6 squared, and that's just going to give us 6. So then if I actually go, well, z1 modulus plus the modulus of z2, that's equal to 5 plus 6, which is equal to 11. Alright, and this is bigger than 10.4, which was our modulus of z1 plus z2 in the first place. Okay, so we verified that, and that looks good. So let's have a look at the second one. So if I have now z1 plus z2, what I get here is I have 2 plus 4, so I've got 6 plus 4i. And then if I want to take the modulus of this, that should be a plus there. The modulus of this is z1 plus z2 square root of. So we have 6 squared plus 4 squared. So that's equal to 36 plus our 16. And that ends up being 2 root 13. Calculator, which is about equal to 7.2. And if we were to do these individually, z1 plus Z2. The Z1 plus Z2 is going to be equal to, if we were to do these individually, so we got 4 plus 9. Okay, I think we're about ready for a little bit of a mini break here. It's having a little bit of an attack. So 4 squared is 16, plus 7 squared, which is 49. This ends up being now square root of 13 plus the square root of 65, and that ends up being 11.7. So we can see that this here is bigger than our 7.2. So again, big tick for verification. Alright. Okay, let's use the principle of mathematical induction to show that the modulus of Z1 plus Z2 plus all the way up to Zk is equal to the modulus of Z1 plus the modulus of Z2 plus the modulus of all the stuff in between and the modulus of Zk. Okay, so the very first step that we need to do is we need to look at Pn. So Pn, in this case, we're looking at our proposition, and that is that Z1 plus ... all the way up to Zn is less than or equal to the modulus of Z1 plus ... all the way up to the modulus of Zn. Right, for n greater than or equal to 1. Integers n greater than 1. Equal to 1. Alright, so we've done that. Our next thing to look at is P1, so our initial case. So if I looked at my left-hand side, what I'm going to have is I'm going to have Z1. Right, and is that going to be equal to my right-hand side? Right, well, my right-hand side is equal to just Z1 as well. So indeed, I do have that my modulus of Z1 is less than or equal to modulus of Z1 because they're the same. Right, so we have a nice little tick there, all good. So now we're going to assume PK. Okay, so we could write that out, but really it's just the same as what we had up in Pn. So I'm not going to write it again, but know that we can use it. So now let's look at Pk plus 1. So Pk plus 1, if I'm looking at my left-hand side, start there, and we can see what we've got. So my left-hand side is now Z1 plus Z2 plus all the way up to my Zk plus Zk plus 1. Alright, but what we can do here is I can actually group, not yet, what I can actually do here is I can group these things. I can go all that and all the way up to there, so Z1 all the way up to Zk. That's one complex number. Right, and the good thing is that we know our triangle inequality holds, so that means this is equal to, I've got the modulus of Z1 plus ... all the way up to Zk plus the modulus of Zk plus 1. That should be plus that. And so this looks a little bit messy, so I'm just going to make sure that we can read that all nicely. So that's a k plus 1 down there. So I've just used my normal regular inequality because this is just one number. I can do that because that's what our triangle says we can do. Now split it up. This is now my pk, or I can use my pk to simplify this. So this is now less than or equal to Z1 modulus plus modulus of Z2 plus ... plus Zk plus our modulus of Zk plus 1. I've now shown I've got each of them individually, and then we can write since P1 is true and pk plus 1 is true whenever pk is true, then we have that Pn is true for n in our positive integers. So we've just used our induction yet again, hopefully starting to see the point of why we did it first, because it does show up over and over again, and it's a fantastic tool for proving things, not only in specialists but in maths in general.